All right, gang, hold on to your butts, because this is Lecture 21, Part 1, Chapter 5, Section 3. And we are going to be talking about energy and enthalpy. These are some high-level concepts, and we are going to have to get through some definition through induction. First off, enthalpy and energy are state functions. Now, a state function is a function only of the state of the system. That's why they use the word state. It means where you are, not how you got there. So another word for it is path independent. Okay. Doesn't matter how you got there. All that matters is where you are. What is the state of where you are right now? Okay. So some examples of state functions are temperature, pressure, volume, the number of moles inside the system, but also to give you something more, visual sort of thing, how far you are from the origin, say, how far you are from another location. Okay, doesn't matter how you got there, you are where you are. Okay, and however far you are from, say, the zero is however far away you are. Okay, so those are all state functions, and also energy and enthalpy are state functions. Now, the alternative to state functions is path functions. Okay, a path function, it does depend on the path. So it's not simply a matter of where you are. Okay, it is a function of how you got there. So some examples of path functions would be distance traveled. Okay, so going back to the nice visual analogy, okay, you have your two locations and the distance in between them. Okay, the distance in between them is a state function, but the distance you've traveled is not a state function. That is a path function. Okay, if you travel the shortest distance, that's the shortest possible path. But you can travel any other path, and thus get a much longer distance traveled. Other examples of path functions are heat and work. Heat is the amount of thermal energy transferred from one system to another, and work is the energy needed to move an object. Okay. So think about a battery. Okay. You hook it up to a wire, and you just short circuit it. See, this is a battery and this is a wire. Okay, so just a wire from the anode to the cathode. You let the energy flow, and what happens? Well, the battery will quickly run itself out and just release a whole lot of heat. Whereas, you take the same battery, you hook it up to, say, let's call it a light bulb. Okay? Okay. The light bulb shines, and what happens? Well, the battery will still run itself out. It will release some energy as heat, but it's also doing some chemical work to get that light to shine. So, even though, you're going from the same beginning point to the same end point, the energy of the full battery and the energy of the dead battery, one way it's all heat, the other way it's doing heat, releasing heat, and doing some work. Okay. So heat and work are path functions, but things like energy are state functions. It's important to know the distinction between path and state functions because it affects a lot of the sorts of math we do. If you go on to study more chemistry, then path versus state functions and things like constant volume, constant pressure become a really big deal. For us, it's less of a big deal, but it helps to understand why some things work the way they do. When I say some things, I mean some of the math problems you're going to end up doing. So having discussed path and state functions, let's talk about internal energy, which we symbolize with the capital letter U. Okay. The internal energy of a system is every single possible bit of energy in the system. Okay. So we're talking thermal energy, we're talking non-random kinetic energy, chemical potential, electrical potential, every single bit of energy inside of a system. And that is U, the internal energy. Okay. And in this case, it also helps to remember the distinction between system and surroundings, because the U, the total energy of the universe, is equal to the energy of the system plus the energy of the surroundings. Of the surroundings. Okay, so every single scrap of energy in the universe is just the energy of the system plus the energy of the surroundings. But more important than that, let's talk about the change in energy of a system. We care about the change in energy of the system because change in energy is really what tells us why things do what they do. So we need to think about the change in energy of the system. But there's also this. Okay, what they discovered through observation was that the change in the internal energy of a system is Q plus W. Okay, the heat absorbed or released by the system and the work done on or by the system. Okay, the sum of those two path functions, so path functions, are equal to this state function. Okay, so that's just kind of a weird thing, but hey, it happens. Okay, remember the battery. The total change in the energy of the battery. In one situation, it was equal to Q1, or it could be equal to Q2 plus that work it was doing. Okay, so different situations, same change in energy, but different paths. So it sort of works out. And it's often possible to measure the heat change of a system and the work change of a system, especially when you're talking about steam engines, which is what they were talking about back in the 18th and 19th centuries. Now, let's go ahead and talk about sign conventions. That is to say, what do positive and negative signs mean? We've already covered that a bit, but let's just go ahead and cover them again. Q is positive versus Q is negative. W positive versus W negative. Okay, so if heat is positive, then that is heat absorbed by the system from the surroundings. Heat negative means heat released by the system into the surroundings. Okay, we are very system focused. So positive always means things, energy going into the system. So similarly, this is work done on the system by the surroundings. And negative work is work done by the system on the surroundings. we've already talked about heat quite a bit, so hopefully you have kind of a handle on that. You know, temperature goes up, temperature goes down, right? But let's talk about work. Like I said, thermodynamics was really developed in the 18th and 19th centuries to help make better choo-choo trains, among other things, steam engines. And so the way they thought about work was in terms of, you know, cylinders fitted with pistons full of gas. Okay, so, you know, imagine, you know, you push down on this this piston, the gas will push back, it'll resist. You're trying to do work on the system. You're having to put energy in to squeeze that gas down. And then you let go of the piston, it'll pop right back out. The gas inside the cylinder will be doing work to push the piston back out. The reason it has to do work is because there is air outside that cylinder. So, you know, it has to push that air out of the way. And the air is resisting it. You know, there's atmospheric pressure. We don't really notice it all the time because we're used to it. But if you popped out of a spaceship, right, at, you know, atmospheric pressure into the vacuum of outer space, I guarantee you would notice that there was no air there. It would be very uncomfortable, and then you would die. So, yeah, air does play a role there. Okay? And the way we think about work in a situation like this is work is equal to negative P delta V. So P here is air pressure, and delta V means the change in volume inside the cylinder. Okay, so this is constant pressure. Okay, and that pressure is the air pressure outside the cylinder. Okay. Now, why the negative sign? Well, simply put, it's because of the way we're talking about change in volume and the fact that we care about inside the cylinder far more than we care about outside the cylinder. Okay, so remember, work on the system is positive, okay, greater than zero. So what happens when you're doing work on the system? Your final volume is going to be less than your initial volume because you're squeezing the cylinder. You're pushing in, okay? And so Vf minus Vi is going to be less than zero. So in other words, it's going to be negative. Okay? But we want work to be positive in that case, so we have to have the negative sign in front of it. And if the system is doing work, then it's pushing out on the cylinder. Or sorry, it's pushing out on the piston's moving out, and thus the final volume is going to be greater than your initial volume, or the change, you know, delta V is going to be greater than zero, or positive. So again, we need the negative sign there because we want work to be negative in that case. Okay. So work is negative P delta V. But work is measured in joules. Does P delta V get you units of joules? Actually, it does. That is the neat thing. Well, I think it's kind of neat. Pressure is measured in atmospheres, or it can be measured as force per square meter, where Newton is kilograms, meters per second squared. Yeah, it's just a measure of force. And volume is measured in liters, but if you put it in scientific units, then, System International, then it's cubic meters. So kilogram meters over meters squared, second squared, times cubic meters. Well, we have some meters to cancel out. Okay. That leaves us with kilogram meters per second squared times meters, or newtons times meters, or just joules. So yeah, pressure times volume is a form of energy. And one way you might think about that is that if you have a sample of gas, okay, then the pressure that gas is exerting, is sort of akin to a kind of energy. And if you have more gas exerting the same amount of pressure, then there's more energy there. Or if you take a sample of gas and you increase the amount of energy contained in there, then it's going to exert more pressure on whatever container it's in. Okay, just like a bomb. You have a sample of gas, you heat it up and heat it up and heat it up. Eventually the container's going to pop because it can't handle the pressure. It can't store that much energy inside of itself. Okay, so yeah, pressure times volume is a measure of energy. So long as, it's newtons per square meter or pascals and meters cubed, cubic meters, then that's the same thing as joules. But if it's liter atmospheres, you're going to have to do some conversion. It's not a huge deal. But we're not going to be doing too much work, no pun intended, with work. Not too much work with work. Because we are more interested in chemical reactions than we are in pistons and cylinders. We are not 19th century engineers trying to make better choo-choo trains. Instead, we are going to talk now about enthalpy, which we represent with the letter H. Scientists are lazy, and they are the best kind of lazy. Okay. Namely, they try to make themselves have to do as little work as possible. So, what they did was they defined enthalpy as U plus PV. Okay, so that makes this a state function, because this is a state function, and pressure and volume are state functions, so PV is a state function. No problem. Okay. And this is just a measure of energy. It's a kind of energy. It's not internal energy, because that's what U is. And it's not pressure volume energy, because that's what we have over here on the right. But it is a kind of energy. Okay. It's a way of talking about the energy of a system. But here's where things get interesting. Because let's stick with symbols you already know. Delta H, the change in the enthalpy of a system, is going to be the change in U plus PV. Now, U and PV are both state functions, so we can separate that, delta U plus delta PV. Now, let's go ahead and do something perfectly valid. Okay? Let's say this system is at constant pressure. That means that delta H is equal to delta U plus P delta V. Oops, forgot the plus sign. So that should look kind of familiar to you. Work is equal to negative P delta V. And this is why we set up enthalpy this way, because delta U is equal to Q plus W, heat plus work, or Q minus P delta V. So delta H is equal to Q minus P delta V, just from from delta U, and then plus P delta V. Only at constant pressure. And thus, minus P delta V plus P delta V cancels out. At constant pressure, delta H is equal to Q. This is a big deal. Okay? Because if delta H is equal to Q, that means this is a state function, and so is Q. If you're looking at a system at constant pressure, heat has become a state function, because work is no longer happening. It no longer matters, I should say. And that is pretty darn awesome, because it means all you have to do is measure temperature changes, and you're getting information about a state function. And you don't even have to measure temperature changes incredibly closely. All you care about is delta T, final temperature and initial temperature. All of a sudden, a lot of chemistry work just got a heck of a lot easier. Because what kind of system is constant pressure? An open beaker sitting on a benchtop. And that is a lot of chemistry. Okay. So enthalpy is a really, really big, powerful tool in the arsenal of just a typical practicing chemist. Okay. Because now exothermic and endothermic, increasing temperature, decreasing temperature, things like that, are no longer measures of a path function where it's interesting but not necessarily incredibly useful, but it's a state function. It's telling you about deep changes within the heart of whatever it is you're looking at. That's really why we care about state functions, because it's related to the state of the system. It's related to the nature of the system itself, and not just what you're doing to the system. All right, let's go ahead and call it here for 21 Part 1. When we come back, we will continue our discussion of enthalpy.